Hello everyone. So we started talking about simple linear regression last time. And so today I want to start off by going through this problem 5 of the homework. You should understand these, but there's really no need for me to go over them. Just look at the solutions. Okay, but so for question number 5, we have data on fuel consumption and load weight for 100 different Boeing 777s. So our goal is to try to better understand the fuel consumption of a plane based on its given load weight. Okay, and so this should be called fuel, and as with all the other data sets, should be under Blackboard course content data sets. Okay, and the easiest thing to do is to pop it on the desktop so that under this Webull analysis code, or wherever you may have put it in a better spot, this last line, you have to modify the username and you have to update what the data set is called, which is just fuel, right? Fuel.csv, commas. If you ever wondered, that stands for comma separated values, which still might not make a lot of sense to you. But anyway, the data set's called fuel. And one thing, I'm going to call my data set fuel.data, okay? During the live lecture that ended because Blackboard wasn't cooperating very well, I originally called this dataset fuel, and now I'm calling it fuel.data for a reason which I'll show you in just a second. So we copy that, paste it, see what fuel.data looks like. The first column is actually called fuel, and so if I call the dataset and one of its columns fuel, that could make the problems a little harder going on. So fuel.data is my data set. This column labeled fuel is my fuel consumption, and this column labeled load is my load weight, right? So this is X and this is Y. And the first thing that it wanted was a scatter plot. So the plot function, you put X first and then Y. Oops. So the first thing I have to do in order to make my life easier is attach the data set, and it's called fuel.data. So now I can use those labels, fuel and load. If you don't attach the data set, you cannot do that. You have to use that thing where you put like a bracket, comma 1, bracket, comma 2, which can be annoying. So plot X is load, Y is fuel consumption. Okay, and so we can see we have our load weight here on the x-axis, which is where we want it, and we have fuel consumption on the y-axis. Okay, you always want your response variable here and your predictor variable here. Okay, if it is the case of linear regression, which is what we're doing. And so you can see we do have quite a bit of scattering, right? The points are clearly not lined up on a straight line, right? However, they're not random. Okay, I say they're not random because if you notice, there's no points here and there's no points here. So as load weight goes up, so does fuel consumption. Although the relationship doesn't look, it's not super defined, like they don't all fall on a perfect straight line, but there is a linear relationship. As one goes up, the other goes up. Because notice we don't have some sort of a curvature. We don't have some sort of a up and down, right? So it does look linear, right? Straight line. It's just not, there's a lot of variability, right? But nonetheless, the relationship is there, okay? And so fit a regression line to the scatter plot. Okay, so we can use, if we go to our ANOVA regression code, okay, go down here to regression, makes it a little easier. So I'll call it reg.model again. And so this is my y variable. You put your y variable here, which is fuel, and then past the tilde, you put your x variable, your predictor variable, which is load weight. Okay, so this is all we need right here. And well, in order to get the line to show up, we need this right here. And as long as we called the linear model, our simple linear regression model, reg.model, then you don't have to modify this code right here at all. and this just tells it to put a line here. Okay, so based on this scatter plot, this red line, this is our line of best fit, right? This is the best possible line in terms of the least squares equation, right? Minimizing the squared distances between each point in this red line, both from the top and the bottom. This is the best possible line, okay? But as you can see, as I've said, there's definitely quite a bit of scattering. There does appear to be a relationship, but it's not a super tight relationship. Okay. What is the regression equation that corresponds to this regression line? Okay, so we called our model reg.model, our linear regression model, so let's just type that in. And we can see that beta naught hat is this, and beta 1 hat is this. So what we have, I'll just put it like this, y hat, right, our fitted value of y, our predicted value of y, is equal to the intercept, 6.791, plus the slope, because it's positive, plus 0.2632 times x. I'll put it like that first. Okay, that is our fitted regression equation. One thing that you can do, you can put it in terms of the actual variables, right? So fuel consumption is y. So fuel is equal to, again, this. And then I'll put times our x variable's load weight. So you could think about it in two ways, right? In a more general way or specific to this example. Of course, you'll always have to eventually, I'm going to ask you to interpret things specifically toward the example. So we can see that the intercept is about a little less than 7, and the slope, right, is about 0.25, 0.26. Okay? So that is our equation. This is the equation of the line, right? Y is equal to 7 plus 0.26 times x. Okay, interpret the estimated regression coefficients, beta naught hat, beta 1 hat, okay? The estimated intercept, the estimated slope. And I'm always going to be specific. You need to, I've put this in terms of a real problem. So treating it as a real problem, right? Assuming that you actually were doing this, you're not going to report to somebody these things in just general terms. You're going to put it in terms of the problem, okay? So that's what we want to do. Interpreting beta naught, I'll just put it like that, hat, right? Okay, interpreting that, which is again the estimated intercept, okay? Right. Kind of we predict that the average fuel consumption, and again, what are the units? We have tons per hour and load weight in tons, okay? So tons per hour in tons. So the average fuel consumption, tons per hour, for a Boeing, how do you spell Boeing? Okay, Boeing 777 that has a load weight of 0 tons, right? This is what the intercept means. It is the average value of y when x is 0, right? The average value of y when x is 0, meaning this goes away. Okay, so the average fuel consumption that has a load weight of 0 tons is 6.791 tons per hour. Okay, And so unlike some of the other examples that we talked about, this makes perfect sense, right? If the Boeing 777 isn't carrying anything, it has 0 ton load weight, then right, it's going to take about 6.8, or it's going to consume about 6.8 tons of fuel per hour. Okay, so beta naught hat, the estimated intercept, does actually make sense in this problem. Okay, the estimated slope, beta 1 hat. Right? We predict that for every, okay, and in general, 1 unit change in x, but we have units, right? For every one additional ton of load weight, right? For every 1 unit increase in x, 1 unit increase, don't know why I put load, in x, load weight, we expect y, which is fuel consumption, to increase. And again, it's increase because the slope is positive. If this was a negative number, then you would simply just put decrease, okay? Increase by 0.2632 tons per hour, okay? So for every 1 additional ton of load weight that our plane carries, the fuel consumption is going to increase by 0.26 tons per hour. Again, of course, this always is interpretable in simple linear regression, but again, very nice interpretability. So both of these, in the context of this real problem, right, have very nice interpretations, and you should be able to understand them in terms of the problem, okay, and not just in some general XY sense. Okay, we interpret it. Does our model appear to fit the data well? Okay, so one thing that we haven't talked about, and we'll talk about later, probably next time, is verifying some of the assumptions, right? We have assumptions on our error term, right? Verifying those. But so that's not really what I'm getting at here. I'm just talking more in the general sense. And as I've kind of said before, right? The relationship does appear linear. There does not appear to be some pattern, some curvature pattern or some up and down pattern, okay? But it's clearly, it's right, it's not it's pretty scattered, okay? So I might put that the relationship does appear to be linear, but there does appear to be a lot of variability in fuel consumption even if we know load weight, okay? And let's see what I have in the solutions here. If I don't remember if I talked about R squared yet. Okay, no, so I'm not specific here yet. Okay. We would like to predict the fuel consumption of a Boeing 787 that has a load weight of 30 tons, right? We know that we're going to have this load weight, and of course we're going to go from point A to point B, and so we need to know how much fuel we're going to need. So again, predicting the fuel consumption when we have a load weight of 30 tons. Where are we? Okay, we go in, right? And this is our regression equation. So fuel consumption is just equal to this plus this times load weight. And so all you have to do is plug in 30 for this. Okay? So I'll type it in here and I'll just copy paste it here. So just put in 30, right? And then that's our estimate. So looks like about 14.7, okay? We estimate that the fuel consumption is going to be 14.7 tons per hour when we have a load weight of 30 tons. Okay, so to predict y, you simply plug in whatever value of x you're interested in, and to get your value. Okay, what would the residual be